It's my great pleasure to introduce our next speaker, Professor Antonio Tricoli. Antonio leads the Nanotechnology Research Laboratory in the Faculty of Engineering at the University of Sydney. His group focuses on the engineering of multi-scale materials with application in future health technologies and renewable energy systems. His talk is today on engineering of multi-scale materials for miniaturized chemical sensors. Thanks.
Thank you for we have actually shown for various applications, going all the way from antimicrobial coatings to biomaterials, super hydrophobic coatings, and that the architecture of the material is as important as actually as the material you're using. Today, I'm going to focus on sensing, a miniaturized chemical sensor. And the motivation for this is that actually the world needs sensor, small sensor, for many applications. This goes from energy, obviously monitoring hydrogen, but actually for environmental reason, imagine pollution, environmental gases, and also medical diagnostics. For example, COVID and SARS, if you look at the number since the first day the disease was reported, take a very different increase in number than SARS before. And the reason was mostly the failure of our capacity to determine who was infected with COVID. Because for SARS, people could just use an airport temperature sensor, and therefore we were able to stop people to travel and spread it around the world. While with COVID, many cases were asymptomatic, and therefore it spread everywhere, and now it's still out of control. And even if sensors are slowly emerging to be able to tell you quite rapidly if you're infected, we're still not able to catch everyone. So this was actually an example of failure of portable biomedical diagnostic. This actually is not just one thing about being able to detect a disease, but biomedical diagnostics has to change from blood sampling to contactless or minimally invasive approaches. And this enables, for example, to detect diseases from the breath or from the saliva or easily collectible sample. So this would change actually, as the potential to change medical diagnostics. But to do that, we have to be able to develop this kind of device. And more of these devices are actually being demonstrated, although very few are yet been able to reach the market. And the reason is that when we look, this is an example, for example, of a COVID portable antigen test. If you think about it, it's not just the sensor, the detector that is here, which often is at the nano or micro scale, but it's all the device. You have to do engineering across multiple scale. So how do you do the sampling? How do you make sure you're not collecting something that actually has nothing to do? And how then do you bring it all down to the preparation? Sometimes you have to dilute it or concentrate it. And then how do you do an accurate detection? So we try to focus across this range actually of activities, processes needs to be done. And that's why when I say about multi-scale engineering of material, is that if you want this to happen on a single portable device, you'll be able to work across all these scales in a very small space. I'm going to give you some examples. Let's start with the sampling of liquid. We have worked on creating materials, very thin materials, like this one. This is 200 nanometer. And these materials, if you place them correctly, this is just silica functionalized with some fluorine groups. They actually can repel water, alcohol, but many other things too. Like, for example, this is, they're omniphobic. They can repel toluene droplets or oil. This is, you will see now a droplet of alcohol, how it bounces off this invisible layer of material that you can create by structuring the surface. So this is important for sampling because if you, for example, put it on a container, you can decant oil. And if you put in a coin, you can even take water apart. So that's the osmosis effect. And if you use a needle, for example, to collect something in a droplet of oil, you will see that the oil immediately sticks to the needle. And if you try to release something like water, this is water with a blue dye, actually the water will come up because of surface tension. However, if you create a super omniphobic needle with the same coating I showed you before, you cannot penetrate the oil. So that's a droplet of oil on an oleophobic surface. Then you can press in your liquid, and it's going to stay there. And you can make cool things such as this is a water encapsulated in an oil droplet with very controlled doses for sampling. There are many other things you can do. This is a so-called rose petal surface. This is a super hydrophobic adhesive state. It means there is no interaction between the surface and your material, but it sticks. And you can use this to move droplets of blood and other things for sampling. And you can also do paperless microfluidic. This is so-called origami and mimosa origami effect. And you can create with this fiber, with this nanostructure, something that when you put a liquid, it can transport it very rapidly somewhere else without the utilization of electricity. And this is just another example. You can mix stuff and you can play with this and do many interesting things. So this was what I wanted to show you, is that by structuring material very carefully, even simple materials like PCl or silica, you can obtain very good sampling. Now I'm going to go to the detection. A few years ago, actually quite a long time ago, we worked on developing methods to produce chemoresistive metal-oxide sensor on wafers. And we worked with companies like Sensirion, and we demonstrated that actually you can deposit very well this sensing layer on large area wafers and with a short process. And then we tried to utilize this material for chemical sensing. And this is an example. We just measured the resistance of this metal oxide layer. And we have two heaters here and a temperature controller that tell us what the temperature is and keep it there. And you can measure down very rapidly down to 1 ppm or less concentration of CO. And if you look at it, this works quite well. So very small response and recovery times. The reason why it works very well is actually, again, the structure. So what we have here is a hierarchical structure of nanoparticle, very porous and open. And this was a sample to show you that if you're able to control the structure of this material, then you're also able to control the performance on the device, a very small device. So one area where I have specialized is trying to create this structure by self-assembly, following similar principle as what you see in nature with fractal. So fractal self-assembly structure. You can see snowflakes, which are very beautiful, or in plants. And the one we use actually is aerosol deposition. So you create an aerosol with a nanoparticle, semiconductor, gold, what you like. And then if you control the diffusion and the settling, this is the Beckley number, you can exactly control the porosity. And this is a simulation, particle dynamic simulation, of what happened in the diffusion regime. So you're almost always in the diffusion regime with nanoparticles. So you create this beautiful fractal-like structure that self-repeat over surfaces. It can actually produce a very reproducible morphology. So we have done this with, so how do you produce the aerosol? One way to do it, for example, you can use a flame, you can use a liquid precursor with metal-organic, for example, or gold or whatever you like. You combust it and you supersaturate it, so you burn all the organic part, condense it, and you have an aerosol of nanoparticles. And then you can use the aerosol deposition to basically, okay, this is a tin oxide crystal, for example, to deposit it on surface very rapidly. This is the deposition on silicon wafer. You don't have to be so close. You can be quite far if you want. And you can see a very thick film deposited in a short time. This is 40 micrometers or something. And if you look at the structure, it's the same structure we have simulated before, very open, 98% porosity, which is very good for gas sensing, for example. It's not good for other things, like if you put it in a liquid, it disintegrates. So then you have to add on, but just to give you an example. Also, these are 3 batches, and this is the sensor response to ethanol. And you can see that actually, this process is very reproducible because the self-assembly of small nanoparticle, millions of nanoparticle, is controlled by the same forces. So you get very reproducible properties. You can also use this method to improve selectivity, which is one of the major issues with metal oxide gas sensor. If you're able, and not always, to produce the right type of nanoparticle. For example, we discovered that silicon-doped tungsten oxide, you can stabilize the epsilon phase of it by putting some doping. And this phase is very selective to acetone. And you can see here the response to acetone down to small concentration, particle per billion, and the response to water and ethanol instead, and water at high concentration is much, much lower. And if you do that properly, we went to Austria at that time, long time ago, with the Innsbruck Medical University and led Professor Anton Mann, and we tried our small sensor and compared it to a PTRMS by breath analysis. And the PTRMS is about 100,000, a bit more. Our sensor, if you're able to scale it up, should be around $100 as a device. And you can see here that when you put the mass cone, and in black you see the concentration of acetone, and in gray you see the one of PTRMS. So quite comparable, both with a little drift. So that was an example of some work that we did a few times ago, and now we are actually trying to integrate this. This is an old prototype, looks very ugly, but it works, where we actually put this acetone sensor and try to measure it and send it to an app. So you can measure actually multiple things, humidity, CO2, temperature, and acetone. And we are trying to increase the number of things we measure so we can use AI and machine learning to get better prediction of actually the concentration of what you're measuring. Now, you can also do other things, and I'm going to talk about the structure and the interaction with light. For example, UV light detection, which in Australia is very important. And there have been recently, or not recently now, but some progress into patches and other type of device that enable you to measure UV. If it's electronic, usually it requires kind of a high voltage, so it's not very convenient. But alternatively, you could also use metal oxide nanoparticle, especially if they have a wide band gap, such as zinc oxide or titanium. They are visible blind. So you only measure basically UV. And that's what we did. It's a very simple measurement, like the one I showed you before. We measure the current at a certain voltage. Once you put the light on, UV light, you see that the current increases. And it doesn't increase a little bit. It increased by order of magnitude, actually 7 order of magnitude. So this enables you to work at very low voltage and detect very accurately UV light. I'm going to show you also that this thing is quite transparent. You can see here a film which is about 10 micrometer. It still has about 70% transmittance, and you can detect a lot of UV light like that. If you look at the spectral response, we respond both to UVA, UVB. We have found a way also to tune this as a function of the material composition that we have. And if you would do the same with a zinc oxide film, which is posed by ALD, for example, the change in photocurrent actually is not order of magnitude, it's a very small change. And the reason is that the structure matters. So once you get this porous structure, you can absorb and dissolve oxygen, almost similarly to a chemoresistive sensor, and therefore you activate all your material, and you have this huge change in current. There are some issues. The absorption and desorption of oxygen is low, so we thought about creating nanoscale heterojunction. So we deposited on this porous film nickel, for example, by sputtering, and we created this structure. You can look into the cross-section, for example, and you can see that nickel is not uniformly distributed, but we reach till the end of the film. And it has a strong effect on the response. So the yellow line is without nickel. And then when we start increasing the nickel, we have a faster response, so we get things in the range of seconds before it was minutes. And this is quite a crude approach with sputtering. We believe that if you were to use something more conformal, we should be able to improve this further. Also, the interaction will likely be interesting if you want to, for example, use this chemoresistive device at room temperature. So this nickel zinc oxide nanoscale heterojunction, without light at room temperature, they have no response, for example, to ethanol. But if you have light, you generate carrier, so you separate them at heterojunction and nanoscale heterojunction, and you can use them for sensing something like ethanol and other gases. So you may have seen the poster below of my student Salishba. We have also tried to use these porous networks of nanoparticles, we call them, and making them more selective. In addition to change the material, one approach is also to make filters. And an interesting type of filter is Metaorganic frameworks. So what we did was quite simple. We tried to compare what happened if we coat our zinc oxide, our sensor of tin dioxide with something like Z8 or another MOF. And the way we do it is just by ALD deposition of zinc oxide on a tin oxide, in this case, film, and then we convert it by chemical vapor deposition. And here you can see what happened if the zinc oxide is 3 nanometer and 10 nanometer in the porous network, is everywhere, and what happened when you convert it to a MOF, to Z8. So you start feeling the structure. And when you do that, you basically start changing the response quite dramatically. Maybe you can see various curves here, but the most important is this one, this graph. So if you look at pure tin oxide responds to NO2, ethanol, and acetone. Now, when you start increasing the Z8, you basically can cut off ethanol and acetone and just maintain the response to NO2. This may be also good for hydrogen because it's quite small. Obviously, there's a question, how do you go and be selective about larger molecules? But that's another story. So just to give you a feeling that if you actually use this filter and you're able to encapsulate it in the three-dimensional structure, you're able actually to obtain quite selective sensor for small molecules. Okay, finally, going a bit away from the chemoresistive sensor, we are also working in this year on other type of detectors. And this one I want to show you is optical type of sensors. And we have found a method to develop very well controlled gold nanoisland on surface in very short time. So we use the same flame, we deposit it on a substrate, but because gold has a much lower sintering temperature, instead of making this fluffy thing, we make island. And we can go here in 2 seconds. We have highly uniform islands distributed over the surface, and we can grow them to bigger and bigger crystals. And if you look at the deposition time, from 2 seconds to 60, we can measure actually the diameter. There is a distribution, and we can also have a control over the equivalent diameter, and the spacing between this structure. And the good thing is that they're highly crystalline, so you don't have to do additional sintering, facet structure. And if you measure in 7 points across a surface of various square centimeters that we obtain in a few seconds, you'll see that the optical properties are quite comparable. And then we have tried actually to characterize this and try to design the field enhancement to say, okay, what if we actually have 2 seconds, 20 seconds, 30 seconds? As you can see, the spacing between these gold nano islands changing, so the electrical field will change. And there is a story about uniform disorder. I'm not going to go into that. But basically, you can produce a uniform disorder, which means on a small scale, it's disorder, but on a large scale, it's reproducible. And that's what we see here. And when you do that, then you can also model, like COMSOL and others, the electrical field between this structure and see at which time you expect to have a stronger enhancement, and then compare this result with SERS, for example, and as a function of time. And we can see that actually we get the strongest response to standard analyte, actually nothing too fancy. It's not one of the best, but it's not too bad neither, considering that you deposit these things in 20 seconds very rapidly. There is a problem when you try to detect gases with this kind of plasmonic kind of nanoparticle. And mostly is that they often rely on the change of the electric environment around them. And gases change the electric environment only a little bit. So when you do that, for example, this is our nano islands that you see here, and we put 4% of ethanol, we see a very, 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 very small, almost nothing shift, right? And if you use another method like beam evaporation of gold, similar or maybe a bit worse. So we came up with the idea, can we actually trap this gas molecule in proximity of the field? And what we did, we deposit the gold nano island with the method I showed you before, and then we deposit fractal particles on the top of it by the same aerosol deposition approaches. And what you see actually is a dramatic change. This was just the gold, and this is the gold with the titanium oxide fractal nanoparticle. You see a big shift at the same concentration, and suddenly, now you're able to detect 4% of ethanol, and actually much lower. We could go down to 0.1% with quite large shift in the resonance frequency, actually down almost to, at 0.5%, we have about 1 nanometer. So this is not too bad. We came to the conclusion that that was, why was it working? So we tried to do some modeling and simulation, but I think we would need, it doesn't go to the next one. No, no, it went. All right. So we tried to model what happened to the electric field. And here you can see on the top only gold. And usually gold has a plasmonic resonator, a small skin depth of about 60 nanometer. It means the field enhancement after 60 nanometer, it goes down very, very rapidly. It's negligible, right? So you don't have any more an active volume. And then we model what happens if we have a chain, a fractal with a dimension of 1, of nanoparticles. Well, interesting enough, there is still some electric field going on after very high distance. And what happens if we have our fractal structures is done with the particle simulation I showed you before. We see that they're actually hotspot distributed much above 300 nanometer. And that was very interesting to observe and explains why our larger volume concentrating the gas molecule where there is the electric field can actually enhance the response. The next things we did, and I hope it doesn't make too much noise, usually it does. Let's see if I can mute this, yeah. We use not one flame, but two. Why should we have the gold on the bottom? We thought maybe we can actually deposit this gold nanoisland over the surface. And what you see here is one flame producing titanium oxide nanoparticle and the other one producing gold. And they mix in the gas phase and deposit together. And what we wanted to happen, it was something like this. This is an artistic reconstruction of one of my students that graduated 2 years ago. And you can see beautiful gold nanoresonator distributed in a dielectric fractal matrix. And this is some SEM images where you see the gold particles, both top view and cross-sectional view, and we can actually identify them. And when you use this approach, we create a three-dimensional metamaterial, and here you can control the thickness and the optical properties. It's interesting that actually the width of the peak does not change much up to 2.9 micrometer, although the absorbance change. And then we start seeing interesting effects like widening and so on. But if you compare the plasmonic shift in the presence of gas, so change in refractive index, and this change in refractive index is the one that we define by putting the gas into the chamber and what expected is not the one on the surface, okay? When you do that, you can see the three-dimensional fractal metamaterial has a much higher response than what I showed you before. And therefore, we were actually able to go down to 0.01%. We're approaching now ppm level at room temperature with this optical sensing technology. Again, we try to simulate what's happening. And if you compare the fractal structure with the gold at the bottom, and actually the fracture with the gold distributed, you can see that we have much more hotspot distributed in the volume. And we believe that these hotspots, because they're also places where the gas can condense, because they are porous, increase the response to the gas. And with this, I think I should more or less finish my presentation. So I show you that by structuring materials in 3 dimensions, you can obtain interesting effect, both for sampling of liquid, for sensing by chemoresistive or electrochemical approach I didn't show today, and also for optical sensing. Thank you for your attention. I'll be happy to try to answer to your questions.
Thank you so much, Antonio, for a very interesting talk. So we have time for 1 or 2 questions. Do you want? Okay.
Thank you for the
Oh, yeah.
Okay. Thank you for a really interesting presentation. I got 2 questions. One is the rate of the fuel which is coming from the flame. Is it important in the deposition of the particles?
The rate of the precursor feed rate, you mean? Yep. No, the precursor feed rate tend to control 2 things. One is the concentration that you get into the aerosol, and then the other one is the high temperature region. So if you increase the feed rate, you make a longer flame, and therefore the particle grows more usually. If you make a smaller frame, you go smaller particle. But what controls the deposition rate are 2 things. One is the concentration in the aerosol, and then the other one is the temperature difference. So only these 2 parameters.
Oh, okay. The second question is, when you are doing optical properties of this fractal structure, do you consider the scattering inside of the fractal structure?
In that simulation, now I don't remember if we did that or not in that specific simulation, so I should ask the student that performed it. I assume not, we may not consider that.
Okay.
My question is on multi-state structure.
Very good question. So usually I have a slide about this. I was trying to make it sure. So what we follow is basically the same as when it snows. You see how snows cover the mountain so uniformly? It's because by Brownian deposition, you have the position of small crystal of snow that self-assemble in the structure. And the mechanism is actually Brownian coagulation without sintering, because the temperature for metal oxide is too low to have a full coalescence of the particle. So the mechanism is just Brownian coagulation, which would lead you in general to a fractal structure of about 1.8 fractal dimension, which is more or less what we measure 1.75 in our films.
All right, okay. Do you have questions? Yeah.
Thank you. I saw that you were offering temperature for. I saw you said that we are.
Well, there are a few options. So first of all, you don't always have to use high temperature. I was trying to get to that slide, but you can use light instead of temperature to activate the reaction. So we are able to perform this under UV light, for example, at room temperature or slightly higher temperature. So you can put a UV LED, for example, and you can use that. If instead you would prefer to use temperature, which has some advantages sometimes, then you can have a micro hot plate heater, like the one I was showing in one of the first slides. So that one, sorry, just a second. This one shows, for example, room temperature, 30 degrees response, you see, with light. And without light, is the black line, doesn't work. And the other one is the things I show you at the start. So sorry, just a second, here we go. So these things. Here is a micro plate. It's relatively standard and simple. So you have a silicon, you etch it from the back, so you make a membrane. On the top, you have 2 platinum heater and a temperature sensor and a set of interdigital electrodes. But yeah, sometimes those things have some issues too.
Can I ask you, Antonio, just one quick question regarding your sample, because it's very porous. Is it robust as well in terms of the stability?
It's quite robust if you don't go and touch it.
No, but
yeah, no, what I'm saying, you're
is
right.
it fragile?
We have used them over the years in the chambers, and you get quite a robust response. There are other issues, like for example, because it's a high surface, you tend to absorb contaminants from the atmosphere, and these contaminants may lead to a drift of your response. So it is important sometimes to disturb them. So you have to do some high temperature and low temperature cycles. But in terms of mechanical stability, unless you really have a physical interaction, they are stable.
Thank you so much. So please join me to thank Antonio. So we should. Thank you so much.